So in 4.1, we use the derivative to find where a function is increasing, decreasing graphically, as well as describe or find areas of concavity. And now we're going to take those pieces and move into more analytical description using relative extrema, meaning relative max and min in a given domain or picture of a graph. So by definition, a function f is said to have a relative maximum or abbreviated REL max at some given value x sub 0 if there is an open interval containing that value for which the y value is the largest value. And basically what that means is this y value is greater than the overall function itself in the given interval for x. Similarly, f is said to have a relative minimum again abbreviated REL min at that given x sub 0 value, meaning it's a numerical value, if there is an open interval containing that number on which the y value is the smallest value, meaning this y value is less than the actual function itself for all x's in that interval. And if that function has either a relative maximum or a relative minimum at some given x sub 0 value, then f is said to have a relative extrema. At that given x sub 0 value. So I'm going to show you some examples here. These graphs are already given. So it says for each function describe the relative maximum, relative minimum, or extremum at a given x value. So I'm going to talk about these ones with the orange dot. So first of all, our classic graph, y is equal to x squared. So if I were to talk about a relative max, what we're talking about is any given value that is a relative maximum, meaning this graph is implied to continue in either direction from negative infinity to positive infinity for x. Okay, my y values will continue to increase without bound. Therefore, I do not have a relative maximum, meaning there is not in this picture a maximum value. However, I do have a relative minimum, and that occurs at x is equal to 0. Okay, it is relative. Okay, so here, when I take a look at this cubic value, remember you're looking for a relative max or a relative min. In this case, we actually have no relative max or min, because what happens here is this actually levels off. There's no actual dip in this graph. It levels off and then switches direction. So this is a point of inflection, which we'll talk about later. In this last one, when we're talking about our values from where we see this graph begin and end, depending on how you're reading this, a relative max will be the highest value that we see, even though this is implied to continue in this direction and this direction. There's no absolute, which again we'll talk about later. Our relative max occurs at this value, is where x is equal to -1, okay, and our relative min occurs where x is equal to 1. So the relative extrema for the 5 functions that were given above occur where the graphs of the functions will have horizontal tangent lines. So I could draw a horizontal tangent line here, meaning the slope is 0, slope is 0. Okay. Relative extremum can also occur at a point where a function is not differentiable, meaning you have a sharp point or cusp. Okay, and in general we would define a critical point or a critical number, which we have been using for function f, to be at a point in the domain of f at which either the graph has a horizontal tangent line or f is not differentiable. So we can actually distinguish between the two types of critical points. We can call them a stationary point and also a critical point, and I'm going to show you the difference here. So a stationary point is a subset of a critical point. Okay, so let's take a look at this graph right here. So what we have is a stationary point, okay, right here, where f prime of x is equal to 0, meaning the slope is 0. So this is a stationary point. Okay, this here also is a stationary point. So it's a critical point and a stationary point. Okay, so if you have a stationary point, this is also a critical point because stationary point is a subset. However, here, this is where f prime does not exist because it is a sharp point, or in this case, it's a cusp. Therefore, this is a critical point, but not a stationary point. So you can call this a critical point, but you cannot call this a stationary point. So when you take a look at these two, critical point, not stationary, because you cannot take the derivative here. This is a stationary point as well as a critical point. So that's what this theorem is telling us, that if we have a function that's defined on an open interval containing some given x sub 0 value, if the function has a relative extremum at some given x sub 0 value, then this value is a critical point of f if either the derivative is equal to 0 or you can't take the derivative at all. So this right here is also considered a stationary point.